Here we go on that score. We're recording. First thing I want to say is to announce that for tomorrow, I'm going to record the lecture ahead of time and not have a Zoom meeting on Thursday, February 1st. So I'll record something tonight. It'll be on things like apparent weight and the next unit of stuff that we're studying on gravitation. Apparent weight will be part of it. I may talk about tides as well, but at any rate, no Zoom meeting tomorrow. Okay, we've learned a little bit about Kepler's third law, and Kepler's third law is that p squared equals ca cubed, and for things that are orbiting the sun, if you measure the period in years and the semi-major axis in astronomical units, that C is equal to 1 year squared per AU cubed. It's just a proportionality constant. I've got some videos or a video that I've recorded where I calculate the period given a semi-major axis and calculate a semi-major axis given the period. And I'll give you a link to that in this unit so that for homework question 7, you'll see me doing some calculations on that. And then yesterday I gave you a sheet that you can practice on those things if you want to, and you'll be able to check the answers, most of them, with the data in the back of your book. If it's got something like a comet or some weird asteroid or something, you might have to look it up on Wikipedia, which is one of my favorite websites. Anyway, no Zoom meeting tomorrow. But we had this, and when Newton got a hold of this, oh, by the way, sometimes we'll write T instead of P for the orbital period, standing for T. But when Newton got a hold of it, this became P squared equals 4 pi squared over G times the mass. I'm going to write mass of the OT and then times A cubed. So that's what Newton's version looks like. Now, if you use G as 6.67 times 10 to the minus 11th Newton meter squared per kilogram squared, and this in kilograms, you have to measure P in seconds and you have to measure A in meters. So just for an example problem of that, let's determine the radius of a geosynchronous satellite. So and actually we'll do orbital radius and altitude. Or actually it's sometimes called geostationary, but I'll write it that way, I guess. Okay, and just in case you didn't know what one of those things is, a satellite in low Earth orbit, which we haven't calculated yet. In fact, our first example will be doing that. But a satellite in low Earth orbit will complete an orbit in about 90 minutes. And when I teach astronomy and we have a stargazing session, something I always try to do ahead of time is look up and see if we have any space station flyovers. And they don't happen all the time, but roughly about half the time you might be able to catch a space station flyover. And so it may tell you, for instance, that the space station will have a visible flyover at like maybe 7:46 p.m., except it would write it as, let's see, 1946. And that'd be on a 24-hour clock. But anyway, I'd say that that's gonna happen. And then there would be another space station flyover about 90 minutes after this. And so Instead, let's see, that'd be 8:15, maybe about 9:15, but it might be more like 9:17 p.m. And the space station does that. Now, it's not always visible because some of its flyovers are during the daytime. And so if the flyovers are during the daytime, as the Earth is turning underneath it, you aren't able to see those things. So that's just the way that it happens to be. And it doesn't always show up at the same place in the sky because it's traveling in this nice, pretty much circular orbit, but the Earth is turning under it. So it'll appear someplace at maybe 7:46 p.m. and you'll look to the east to or the west to see it appear maybe. And then during the time that it has taken to orbit to the next one, the Earth will have turned to the eastward, and you have to look farther west to see it. And eventually, it'll be so far west in its orbit that it's not above your horizon anymore until daytime. So that's something that may happen. But that's just something that happens with low Earth orbit satellites, maybe a 90-minute orbit. Okay, well, the moon takes 27.3 days to orbit. This is the moon. Okay, so in between 90 minutes and 27.3 is 24 hours, or actually the time that it takes the Earth to spin on its axis is about 4 minutes less than 24 hours. But here's what happens. We'll imagine we're looking down on the Earth from above the North Pole. So here's the North Pole right there. And Earth is turning toward the east. So a satellite in low Earth orbit goes roughly 17,000 miles an hour. Okay, Earth's equator moves toward the east at about 1,000 miles an hour. That's why we launch satellites to the east all the time. You get the first 1,000 miles an hour for free. But anyway, Earth is turning in that direction, and something in the low Earth orbit only takes 90 minutes to get around. The moon way out there takes 27.3 days to get around. Well, someplace in between there, you can get a satellite at an orbit and you park it above the Earth's equator, and it takes exactly as long to get around the Earth as the Earth does to turn on its axis. And that's what a geostationary satellite happens to be. So if you're at some point on Earth, and there's a whole bunch of them up there, but if you're on some location on Earth and you've got some kind of an antenna, you can aim it at one of those things. And as the Earth turns, that thing is always in the same direction as far as your satellite dish is concerned. And so you don't have to change the aim of it. And that's what a geostationary satellite is. And if you've got Dish Network, or I forget what the other one is, DirecTV maybe, I can't remember. Anyway, we had Dish Network for a long time, and we got a satellite dish mounted on our house, and it worked just fine. Except then we found we don't watch that much television anymore. But let's figure out the orbital radius and altitude for a geostationary satellite. Well, we know what the period's going to be, but we need to get it in seconds. It'll be 23 hours, 56 minutes. And if I take 23 hours and multiply that by 3,600 seconds per hour and add to that 56 minutes times 60 seconds per minute, I'll get the number of seconds. And the period, I think, is 86,400, but I'm not sure. Actually, it won't be quite that because we've only got the 56 minutes, but 56 times 60. Okay, 86,160 or 8.62, close enough, times 10 to the fourth seconds. So there's our orbital period. Oh, by the way, the M sub OT here, that stands for the mass of the orbited thing. So Earth is the orbited thing in this case. Okay, well, A cubed is going to equal P squared times G times the mass of the orbited thing divided by 4 pi squared. And actually, on a lot of these problems, we go ahead and calculate this, but 4 pi squared over G. Oh, well, we'll plug in the numbers here. So A cubed is going to equal 8.62 times 10 to the fourth seconds, and we have to square that. G, 6.67 times 10 to the minus 11th Newton meter squared per kilogram squared. Oh, this one's kind of a pain to do all this stuff. The mass of the orbited thing, which I have to pull my book back, and it's 5.98, I think, for the mass of the Earth. 5.97. Okay. Times 10 to the 25th kilograms. And you have to divide by 4 pi squared, which we can handle. Okay, unit-wise, how's this going to work out? Well, we've got seconds squared here. A Newton is a kilogram meter per second squared. So the seconds squareds in the Newtons on the bottom are going to go away with those seconds squared. So don't have to worry about that. I still have kilogram meter cubed over kilograms squared, but I'm multiplying by kilograms, so I'm going to end up with meters cubed for units. That's good because it's A cubed. And Kepler figured this out for elliptical orbits. We're just going to treat most of the orbits today as circles, and so we just won't distinguish that. And also for a geostationary satellite, it is a very circular orbit, just a little bit of deviation, so not much. Anyway, square that thing. And for A cubed, I get 7.49 times 10 to the 22nd seconds cubed. I have to take the cube root of that. So A itself, where's my divided by thing? One thing I don't like about this calculator is in many light conditions, it's almost impossible to read the multiplication thingies on it. Okay, this would be 4.21 times 10 to the 7th meters. Now, the radius of the Earth happens to be, whoops, look it up in here again, it's not the same at every point on the Earth, but 6.38 times 10 to the 6th meters. And so if I divide this thing by that, I'll find out how many Earth radii it is out there. And just to give you a sense of scale, it's about that orbital radius is about 6.61 times the radius of the Earth. And so that means the altitude, that's the orbital radius. So if you've got the Earth sitting here with 1 Earth radius. That satellite is out there 6.61 times the radius of the Earth away from the center of the Earth, which means its altitude is 5.61 Earth radii. So that's just a little bit about using Kepler's third law to figure out the orbital radius of one of those satellites. So that worked out okay. Okay, I had some notes I kind of wanted to go through with you relating to energy and orbits, and then we'll start playing around with some more orbit problems. I'm going to start. The other day we found a new expression for gravitational potential energy, and it's minus g times the mass of the big thing times the mass of the little thing divided by their separation. And so that's gravitational potential energy. And if we're talking about something with respect to the Earth, we'd just put an m sub e down here and have the mass of the Earth, and then whatever the mass of the satellite. But a lot of times we're going to ignore this little m, or we'll make it divide out. Now, we also know that kinetic energy is equal to 1/2 mv squared. So if you have something that is orbiting in like Earth orbit or something like that, so we'll pretend that we've got something orbiting the Earth, the total mechanical energy for an orbiting satellite is equal to the sum of those two things. So it's just going to be, I'll call this TME, and it's going to be 1/2 mv squared minus g m little m over r. And so, okay, you've got the difference of those things. And this is that new definition for gravitational potential energy where it's negative until you get to an R value of infinity, at which point it's equal to 0. So you're always in the hole on gravitational potential energy. Now, something else we can do here is that we can monkey around with Newton's second law, where we have the force that's acting on that satellite is going to be g, mass of the Earth, mass of the satellite divided by r squared. And that force has to provide the centripetal force that keeps the satellite in orbit, which is going to be m times v squared over r. Now, this is another way. This is centripetal acceleration. We can also just say F equals ma, and that's what the acceleration of the satellite is going to be. So we can do something like that. And if I multiply both sides by r here, I can write that mv squared is equal to g times the mass of the Earth times the mass of the satellite over just plain r. Okay, and I'm using that because I want to substitute into this expression for mv squared. And what I'll get is the total mechanical energy is going to be 1/2, instead of mv squared, I'm going to write it g times the mass of the Earth times the mass over r minus, here I've got gmm over r, but I'm going to write it as 2gmm over 2r. That's the same thing. So That way I've got a common denominator here, and I'll have g m sub e m minus 2g m sub e m, or that total mechanical energy ends up being minus 1g m sub e m. And check that if you don't believe me. Over 2r. Okay, or it's equal to minus 1/2 times g m sub e m over r. So when it's in orbit, it's got a negative gravitational or negative total mechanical energy of that much. And to get it to have a zero or positive total mechanical energy, you'd have to give it an energy equal to that. And maybe give it kinetic energy. So that way it would escape from the Earth. But that's a nice little expression for total mechanical energy. Also, something that we had here, this mv squared equals that. Now, this is an orbiting satellite with a radius of r, so we can look at that. Mv squared equals g m sub e m over r. If I divide the m's out, I get that v squared equals g m sub e over r, or the orbital speed is equal to the square root of g m sub e over r. The farther out the orbit is, the slower the orbit goes. Okay. That's something that happens. So if somebody asks you, why does the moon take so long to get around the Earth? Well, there are two answers to that. One is its orbital radius out there is about 60 Earth radii, which means circle that it travels in its orbit is about 60 times as big as the orbit that an Earth orbiting satellite in low Earth orbit, maybe only a few hundred kilometers up there or a few hundred miles, the moon has to travel about 60 times as far, but that's only part of the reason it's also going slower. Being 60 times farther away, this radius is going to be 60 times as big, whatever the square root of 60 happens to be. It's about 7.7. So the moon's only going to go about 1 over 7.7 times as fast as a satellite in low Earth orbit, or about 1/8 the speed. So 60 times farther and at 1/8 the speed, approximately. That's why it takes so long to get around in its orbit. Okay, I've got some example problems. One of these was in the let's see, in the set of problems that I looked at yesterday, but or 2 days ago, but I didn't want to do it until we had learned about orbits. So here we have it. Low Earth orbit satellite, altitude above the surface of 380 kilometers. So we need to figure out its orbital radius, and that'll be, let's see, radius of the orbit is going to be the radius of the Earth plus that altitude. So orbital radius, let's see, 6 point, and again, I can never remember, is it 6.37 or 6.38? I think I've got them on the wall in the front of the room, if I remember right. 6.38. It's actually 6.38 times 10 to the 6th meters. That altitude, 380 kilometer, would be 380,000 meters, or 0.38 times 10 to the sixth meters. So I can just add that onto here, and the orbital radius is going to be 6.76 times 10 to the sixth meters. So now I know the radius. We can figure out the orbital speed first. We just developed an expression for that. It's g times the mass of the Earth over r, square root of that. So let's go ahead and figure out the speed. And I'll have choices for how to get that orbital period then. So g is well, write it in variable form first. G times the mass of the Earth over the radius. And that will equal 6.67 times 10 to the minus 11th Newton meters squared per kilogram squared. All the time with that. Mass of the Earth, 5.97 times 10 to the 24th kilograms. And I think when we take this next test on gravitation, I'm going to, dog hair everywhere, copy this out of here and give it to you. So you'll always have that data that you might need. Okay, and I'm dividing by that radius, 6.76 into the sixth meters. Okay, let's see. This is kilograms squared on the bottom. A Newton is a kilogram meter per second squared. Let's see, I'm pretty sure. Kilogram meter per second squared. Meters. Kilograms go away. Yeah, and I'd have meters squared per second squared left under the radical, which is meters per second. So we're good to go there. Stop and check those units every time. Mm, 24. And get 7 point, can't tell if it's 6.7 or 6.8, but I'll just say 6.8 times 10 to the third meters per second. And just to get a feel for how fast that is, I'll convert those units into, let's see. Well, 3,600 seconds per hour, and then 1 mile over 1,609 meters. I know I probably shouldn't convert to American units, or imperial units, I think they're called. I want to store that thing first. Whoops. Oh, rats. Oh, well, just deleted it by accident. 0.68. Okay, it's about 17,000, actually about 17,200 miles per hour. And so pretty good clip. Okay, now what about the orbital speed and orbital period? Well, you could use Kepler's third law to figure out the orbital period. Okay, that'd be one way. You'd go the p squared equals 4 pi squared over g times the mass of the Earth times a cubed. And so you could plug all those numbers in, or you can think, oh, it's traveling in a circular orbit. The speed is going to be 2 pi r, the circumference of the circle, divided by the orbital period, or the period is just going to be 2 pi r over v. And I'd rather do this. I don't have to plug in all those complicated numbers anymore. So 2 pi times the radius of the orbit, 7.68 times 10 to the third. Whoops, that's not the radius of the orbit. That's v. 6.76 times 10 to the sixth meters. And I divide by that speed, which I just figured out. Times 10 to the third meters per second. Okay, so 6.76. And meters divided by meters per second is going to, I get an orbital period of about 55, 30 seconds. And if I convert that to minutes, it's about 92 minutes. So roughly an hour and a half. A little bit longer than an hour and a half. So low Earth orbit, about 90 minutes, something like that. So in getting from Earth's surface to an orbit at this altitude, what fraction of the escape energy from Earth's surface did it require? Okay, here is its speed at that orbit. The other day we calculated an expression for escape speed from Earth that looked an awful lot like that. The escape speed is equal to the square root of 2g times the mass of the Earth divided by the distance from the center of the Earth. Now, the distance from the center of the Earth for this thing is a little bit more than the radius of the Earth. And so maybe I could take that into account or not. It's not going to be that different in the expression for escape speed from this distance as opposed to the radius of the Earth. This isn't a huge difference. It's 6.38 times 10 to the sixth versus 6.76 times 10 to the sixth. Although we could monkey with that if you want to, but I wanted to show you something. That's the escape speed expression. The speed that we've got for this thing is a lot like that, but it's g times the mass of the Earth over the radius of the Earth. And if I put this thing on top of that thing, so v over the escape speed, you end up with the square root of g mass of the Earth over the radius. Since I'm dividing by that fraction, I can multiply by it, and I'll have r over 2g times the mass of the Earth. And everything divides out except for a 1 over the square root of 2, which when I was in high school and we had to calculate trig functions by hand, I got used to doing this. You rationalize the denominator. It's the square root of 2 over 2. Square root of 2 is 1.414. That means this thing is actually going to be 0.707 is what it is, or the speed is 0.707 times the escape speed. So the satellite is going to be going roughly 70% of the escape speed from Earth. So you've gotten it most of the way to getting it away from the Earth just by giving it that particular or putting it into orbit. 70% of the way there, 71% almost. So that's kind of a neat thing about satellites' orbits. This one's a little weird, but I may save that one for later. And yeah, save that for later. But what is the minimum speed necessary for a spacecraft to escape the solar system starting at the Earth's orbit? So we're going to use that escape speed thing here, but this time it's going to be trying to get out of the solar system, and it'll be 2 times g times, this time not the mass of the Earth, because you want to get out of the solar system. It's going to be the mass of the sun down here. And then you're starting from the Earth's orbit. So Earth's orbital distance, or orbital radius, Earth has the most circular orbit of any of the planets, but still a little bit of variation. It's 1 astronomical unit, which is about 1.50 times 10 to the 6th kilometers, which would be, no, it's 150 times 10 to the 6th kilometers, 150 times 10 to the 9th meters. It's 1.50 times 10 to the 11th meters. And I better look that up to make sure I did that right, but I think I did. Orbit radius in meters, yeah, 1.5 times 10 to the 11th. So that's what it happens to be. The mass of the sun, I'll look this up, but it's about 1.9 something, 1.99 times 10 to the 30th kilograms. So got some big numbers that are going to be showing up in this thing, but then that capital G brings it back down. So the escape speed from there, there's our variable form. Here's our number form, 6.67 times 10 to the minus 11th Newton meter squared per kilogram squared. And we've already gone through the unit stuff on this, but I'll go ahead and do it again. 1.99 times 10 to the 30th kilograms. For the lab, Jupiter's mass is about 1.90 about times 10 to the 27th kilograms. So it's just about 1,000th that mass. And then that R, 1.50 times 10 to the 11th meters. Okay, so it's plug and chug. A Newton is a kilogram, meter per second squared. That meter is going to divide with that. This kilogram, that kilogram, we'll divide with those kilograms, and we'll have meters squared per second squared under the radical, which is a good unit for an escape speed. So and I get about 4.21, I guess I've got 3 sig figs, times 10 to the 4th meters per second. Oh, seems like a lot. Okay, that's quite a bit. It's 42.1 kilometers per second. Remember, escape speed from Earth was 11.2 kilometers per second, about. However, you get the first 2.9 times 10 to the fourth meters per second for free. And the reason you do is because Earth's orbital speed around the sun happens to be about 29,000 or real close to 30,000 meters per second, is 3 times 10 to the fourth meters per second. So it's not as bad as it might seem. So kind of fun things anyway. Okay. Voyager 1 achieved a maximum speed of 125,000 kilometers per hour on its way to photograph Jupiter. Beyond what distance from the sun is this speed sufficient to escape the solar system? Well, there's our speed that we happen to know, so we can call that an escape speed. Let's see. Looks to me like that's 1.25 times 10 to the 1, 2, 3, 4, 5 kilometers per hour, and I need to fix that, so I multiply by 10 to the third meters per kilometer, and 1 hour over 3,600 seconds, and I'll get meters per second out of that. And it's about 3.47 times 10 to the fourth meters per second. So we want to know if V sub E is equal to the square root of 2 times G times the mass of the sun over R. We want to know what R is, where the escape speed would be that. And we can convert it into astronomical units and when we're done. So if I square both sides, I get V sub E squared is going to be 2G mass of the sun. Oops. Anyway, 2G over R, or that R will equal G times the mass of the sun divided by that V sub E squared. Let's see the units on this. 6.67 times 10 to the minus 11th. Let's see, a Newton. I'm going to write out the Newton as a kilogram meter per second squared. Okay, so Newton meters squared per kilogram squared. Okay, and then down here, oh, I've got the mass of the sun, 1.99 times 10 to the 30th kilograms. And on the bottom, I've got that speed there, 3.47 times 10 to the fourth meters per second, and I square that. Okay, on top I've got kilograms, kilograms, kilograms squared, those go away. I'll have meters squared per second squared. I'll have meters squared per second squared down here, and there's a leftover meter here. So we'll get that orbital radius in meters. So let's see. I need to figure out a way to store capital G and just pull it out. In fact, I know how to store stuff on here. Anyway. Second answer squared. Okay, I would get 1.10 times 10 to the 11th meters. What are we doing this one? Starting in Earth's orbit. Hmm. So let's see. Oh, well, let's go ahead and convert that into, actually, that's a fraction of an astronomical unit. It's about an astronomical unit was 1.50 somewhere. A couple problems back, I did an astronomical unit thing anyway. And if I divide that, it's going to be 1.10 or 11/15 actually of an astronomical unit. So, but it's a lot farther out than that when it was on its way to Jupiter because it wasn't any closer than 1 astronomical unit. So it was going fast enough even before it got to Jupiter to escape the solar system. And it got a gravitational boost from Jupiter on the way out there. I wanted to show you something. Let's see. You can go to a NASA website and look at the mission status for the Voyager spacecraft right now. And it's kinds of stuff. The launch date, elapsed time for the mission, its distance from Earth in kilometers and astronomical units, its distance from the sun in kilometers and astronomical units. That's Voyager 1. Here's Voyager 2. Maybe interesting little thing here is that Voyager 1 was launched, well, a couple weeks after Voyager 2, but it's a lot farther from the sun. It got gravitational, Voyager 1 got more gravitational kicks from the outer planets than the Voyager 2 happened to. By the way, 162 astronomical units. Pluto's orbit is the most elliptical of all the planets. At its near approach to the sun, what's called perihelion, it's about 29 astronomical units from the sun. At its distant approach, or distant part of its orbit, it's about 49 astronomical units from the sun. So Voyager 1 is more than 3 times farther away from the sun than Pluto is at its most distant point in its orbit. So it's a long ways out there. And it's still going at just about 17 kilometers per second. And way out where it is, the gravitational pull from the sun is so weak that it's barely being slowed down. So something kind of neat about what's going on with those things. I hope you can see that. Here's a little picture of the two things. And you can see the instrument status on the things. They've still got instruments that are working. They've got some that are not working. The plasma science instrument doesn't work anymore. A lot of things don't work anymore. Something that we didn't study was that, oh, here's a roughly what Voyager's craft was, or orbital path was in the inner solar system. By the way, you can just track this down. If you look up where is it now, Voyager 1 and 2, and go to the NASA site, you can come right to this thing and it'll show you that. So where is it now? Yep, there it is. It's hard to say. Okay, let's see. We'll get back here. Come back to visualizer. I did the one on the back of that. Done almost all of these. Okay, here's a weird little problem. In the Bohr model of the ground state of the hydrogen atom, the electron and protein are separated by 5.28 times 10 to the minus 11th meters. If the only force between them were gravitational, What would be the period of revolution of the electron orbiting the proton? Okay, it's not. The electromagnetic force or the electrostatic force in this case is so much larger than this that you can completely ignore gravity. But let's just pretend for this. So if Kepler's third law worked for a situation like this, you'd have 4 pi squared over g times this time the mass of the proton. So mass of the proton times a cubed. And a in this case would be 5.28 times 10 to the minus 11th meters. So all we have to do is just plug this stuff in, and I guess we could solve for p and just take the square root of the whole thing. So I'll plug in the numbers here. 4 pi squared, 6.67 times 10 to the minus 11th Newton meters squared per kilogram squared. I'm getting so I can just rattle those off. Mass of the proton, 1.67 times 10 to the minus 27th kilograms. We don't need the mass of the electron here because we're using Kepler's third law, and the mass of the thing doing the orbiting doesn't matter. So 1.67 times 10 to the minus 27th kilograms. Lots of negative exponents down here. And then, let's see, a cubed, I guess I may as well stick it on top. There it is, 5.28 times 10 to the minus 11th meters, and we have to cube that. So on top, we'll have meters cubed. On the bottom, Newton meter per second, or a kilogram meter per second squared. The kilograms will divide out. I'll have meters cubed on the bottom, meters cubed on top. Oh, and there were per second squared left on the bottom, which come up top as seconds squared, which when I take the square root of this will just give me seconds. So it works. Okay. Start off with a big parentheses. Boy, have to pay. Oh, shoot. I didn't pay close enough attention. uh, 5.28 times 10 to the minus 11th, caret 3. Okay, you guys are probably already done with this by now. Hopefully I did this right. Uh, I get a long orbital period. 5.22 times 10 to the 7th seconds. uh, wow. If it had been only gravity acting on the electron in the atom, um, it'd be going pretty darn slow. I That'd be 14,000 hours. So if I divide by 24, I get about 603 days. So yeah, 603 days for the electron to orbit the nucleus of the atom. So just kind of a nonsense problem because we know the electric force is way, way stronger. And when you get down to that level, the idea of electrons orbiting the atom is incorrect anyway. Their behavior is far weirder than that, which we've learned through quantum mechanics. So that's good enough. The last one is something that you could maybe try on your own. This would be a good example problem. You can calculate the acceleration due to gravity. We did this, or I did this a couple days ago when we first started gravity, the acceleration due to gravity on a neutron star. Now, the weight of a 70-kilogram man on its surface, once you know the acceleration due to gravity, you can calculate that. And then find the energy needed to remove a neutron of mass, that mass from its surface to infinity. Actually, that would be the escape speed formula. And that's 2g m over r. And we can calculate that. Its mass is that of the sun, but the r is only 10 kilometers, 10,000 meters. So let's go ahead and, oh, it wants the energy needed to get it out of there. But, well, that would be v sub e squared is going to equal 2g capital M over r, 1/2 the mass of the neutron times v sub e squared. I'd stick a 1/2 the mass of the neutron here, and the 2's divide out, and I'd get capital G times the mass of the sun times the mass of a neutron divided by the radius of that star, and that would be the escape speed for a neutron, or escape energy to escape from the neutron star. So we can plug in the numbers on that. But for extra practice on some other ideas, see if you can calculate this and that. And then we'll stop after this one. So 6.67 times 10 to the minus 11th Newton meters squared per kilogram squared. Getting tired of chunking these things out. I'm going to have a kilogram and a kilogram over here. So the mass of the sun, 1.99 times 10 to the 30th kilograms. And then I also have to multiply by the mass of a neutron. This is the same as the mass of a proton, by the way, to 3 sig figs. 1.67 times 10 to the minus 27th kilograms. So between the kilogram here and the kilogram there, the kilograms there are gone, and I'll have Newton meters squared divided by that distance, which is just 10,000 meters, which is a kilometer. And so what I'm going to be left with is Newton meters, which are joules. That's good. So let's see how many joules it is. Whoa. Pushed a wrong button. Okay, not much energy, but I get 2.22 times 10 to the minus 11th joules. And if I multiply that by, to convert this to a maybe more appropriate unit, although this is probably what they asked for. If I multiply that by, let's see, 1.60 times 10 to the minus 13th mega electron volts. Whoops. I wanted that elsewhere. 1 mega electron volt. over 1.60 times 10 to the minus 13th joules. That was the way I wanted to do it. So I'd get, we did a problem with MEV a while back. Okay, it's about 139 mega electron volts. And so at this level, that's a more appropriate unit. You don't have to mess around with monstrous exponents on things. Still kind of a crazy problem. And but that's a pretty large amount of energy for a single neutron that you'd have to give it to get it off of that neutron star. All righty. We looked at quite a variety of problems today, but having to do with energy and orbits and Kepler's third law and lots of things like that. Mentioned at the very start, but not all of you were here. I'll make an announcement on this. I'm not going to have a live Zoom meeting tomorrow. I'm going to record the material that I would have done tomorrow, probably on a video tonight. So I'll have that video posted in the morning. And we won't have a Zoom meeting tomorrow. And let's see, I may try to set up a review session for our gravity quiz. Really, it's not so much a test, but it might have 4 problems on it, something like that, and we'll have that Tuesday. And then we can gather data for the Jupiter's Moons Lab, which you could start doing yourself if you want to download that software. But anyway, no live Zoom meeting tomorrow. Just watch for a post to a video that you can watch. Okay. I'll stop the share, stop the recording.